Hi, today we are going to learn the basic concepts which we are going to use while studying electronic devices. So, the video will be distributed as follows. First, we'll learn about the units, then, we'll learn about current, charge, and voltage, power energy consumed, passive sign convention, independent and dependent sources, conservation of energy, and Tellegan's theorem. So, let's get started directly. So, units. So we have the following units. So you have on the positive side of tens, you have kilo, mega, giga, tera. And on the negative side of tens, you have milli, micro, nano, and pico. Why do we use this? So what happens is in some devices, the current which you want is very less. And every time writing 0.000013, let's say ampere of current, if you want to write, rather than that 1 2 3 4 5 6, I can write 1.3 microampere because I moved the decimal point 6 times. So 1.3 microampere is a better representation than this. So that's why we have the following numerical system. So we have devices which can work on milli, micro, nano, and pico, like transistors, and we have the commercial things like you have fans, you have TVs, and so on. And when you see that, you use kilo, mega, giga, and tera depending on the type of electronic component you are using and the power it is rated for. We will learn more about this, but these are things you should be knowing. Now let's come to the main thing: current, charge, and voltage. So to define this, we need to define what's an electric circuit. Electric circuit is basically an interconnection of electric components. Okay. Positive charge flows due to voltage. Now you might say that electron is the fundamental unit of charge, and because the electron force flows, it is negative. But then we assume that we use a positive charge. That is our basic assumption. Okay, so let's say you have component 1, component 2, component 3. You have connected it. Maybe you give a voltage V1, V2, and V3, and this constitutes an electronic circuit. Now, what is current? Current is nothing but charge flowing per unit time, or in differential terms you write it as dq by dt. Charge is represented by, current is, the unit is ampere, charge is coulomb, and time is second. So it will be 1 ampere is nothing but 1 coulomb per second. One small point to note is whenever we are going to use small letter, it's a time variant signal. That is, the quantity is going to change with time. But if it is an independent one, we are going to use a capital letter. This is what we are going to use to represent. Also, one more thing to note. Let's imagine we have a wire, and this is the end A and this is the end B. And let's say 5 coulomb of charge moves in this direction from A to B. So IA is 5 coulomb from A to B. But the same thing from B to A is minus 5 coulomb. Therefore, it can be concluded direction, magnitude, both are important to describe current. Okay, I can't describe current only with magnitude because I don't know which direction is my charge is flowing, positive charge flowing, but also I can't describe only with direction. I need magnitude saying how much ampere is it flowing. Both are important. So you have direct current and you have alternating current. Alternating current, this is usually used in fans, AC, and this is what you get in house. Direct current is used for a lot of other things like transistors and so on. So this is something which you want to know. Okay, this is a time, this is a current graph. Direct current is the current will remain constant. It is represented by a capital letter. Alternating current is going to be a sinusoidal wave, and we have other ways of representing it, which we will come to know later. This is the current. Now, voltage between 2 points is the energy required to move it from point A to point B. Here it refers to positive charge. Please remember it's a positive charge. So to give a basic example, just imagine you have a ground, you have a mass, you have a ball. So when you leave the ball will come down. Why? Because there is a gravitational field acting on the ground. Similarly, if this thing had to be a positive charge, the thing which will pull it is the electric field, and voltage is a representation of the electric field. Okay? So voltage can be described as energy required per unit charge, that is joule per coulomb, and the SI unit is volt. Now consider this circuit. This is some circuit. From point A to point B, the voltage is 2 volts, or VB is nothing but minus 2 volts because one is higher than the other. Now let's come to the power and energy consumed. These are the two fundamental things we need to see. So let's take a very basic circuit, which we all know. You have a flashlight. In a flashlight, you have a bulb, you have a battery, and you have a switch. Now, if the switch is open, the current won't flow because there is no path for this current to flow. The minute you press the switch or you close this connection, what happens is that electrons start moving and the light glows. The chemical energy in the battery is converted to light by the bulb. Now, because it's a positive charge, if this is the positive terminal of the battery and this is the negative, so the battery will push the charge from its positive to negative end because it's a positive charge. Okay, this is something we need to know. So the voltage is work done per unit charge, or if we do V into I, that is dW by dQ into dQ by dt. So it is dW by dt, that is power. Okay, so power is nothing but V into I. This is one formula which is very important. Another thing is work done is integral the power or integral voltage and time throughout the entire length from T0 to T1. This is something you need to know. The next very important thing is passive sign convention. What is passive sign convention? Let me tell you. So you have an electric component and now you want to find whether it supplies energy or whether it absorbs energy. Or in simple terms, you want to know whether it's a battery or whether it's a bulb. Okay? This is a very vague way of saying it because sometimes this battery can actually absorb energy rather than supplying when connected to a more powerful battery. That's why when given a component, you want to know whether it's supplying the energy or whether it's absorbing energy. Okay, so let's come to the basic circuit which we had, a flashlight circuit. You have a battery, you have a bulb, and you have a switch. Now let's break the circuit. Let's look at it from perspective of a battery. What is the battery doing? You have a positive and a negative. If this were to be a black box, you see that current goes from the positive terminal and comes to the negative terminal. Similarly, for a light bulb, if this were a black box, okay, and you have negative and you have positive, the current comes from the negative and goes through the positive. Sorry, the current comes from the positive and goes to the negative. Am I right? It comes from the positive and goes from the negative. So now what we do is we assume that what we are dealing with a light bulb every time, because in a practical circuit there will be more light bulbs than there will be a switch. I mean, there will be a battery. This is very important thing to understand. Okay, so this is passive sign convention. Now assume that the element is consuming energy. If your assumption is true, if your P is positive, your assumption is right, else your assumption is wrong. What I mean by this is, You, let's put it like this, you assume current enters through positive. Okay, and then you calculate V into I, and if that V into I is positive, it means your assumption is correct and it's a passive, else it is supplying energy and it's a battery, something on those lines. So let's come to this question to understand it further. So you have this element E and you have a current which is entering the negative and positive. The voltage across this is 2 volt. So what we do is we calculate V into I. Okay, if this was a bulb, the current should have entered the positive fucking terminal. So here the current is entering the negative terminal. So what we do, we reverse the direction of the current. So we reverse the direction of the current, and now the current for us becomes minus 4 ampere. So P equal to 2 into minus 4, that is minus 8 watt. Because this is minus, that means E is a battery, or E is an element that is supplying energy to the circuit. Am I clear? We need to solve numericals, and hopefully at that time you'll understand. Now we have independent and dependent sources. What is an independent source? Independent source is current. So you have a current source and you have a voltage source. So for current source, the current source maintained a specified current across two terminals regardless of the voltage. So if I have this connected anywhere in the circuit, that means that this branch is gonna have 3 ampere regardless. No matter what voltage I connect to it, it will have 3 amps. Similarly for voltage volt, if I connect this to a circuit, this thing is gonna be 5 volt regardless of the current it lives out. Now what you need to note is these are ideal devices. Ideal devices is this does not happen in practical. In practical you have devices that have ranges saying I can, for a voltage source you have a range of current saying above this current the voltage will drop. Similarly for current source you have range of voltages saying only till this voltage to this voltage it's stable, or else the current will drop. This is something we need to consider, but for now we can use ideal because we will make sure the condition which we are using it is ideal. So next is you have a dependent source. Dependent sources, you have a dependent voltage and a dependent current source. So you have a location in the circuit. Let's say there's circuit IA. So this voltage is dependent on this current. Or sometimes you have element plus or minus V, and the voltage of your source is dependent on this voltage. Similarly for current. Why is this important? So you have some devices like transistors, and while modeling them, you would use this concept where the current in one of the terminals will decide the voltage in the other terminals, and so on. Something on those lines. You need not break your head for this, but this is something we use to model transistors, which we will see later. Now you have energy conservation slash Tellegan Theorm. We assume that energy is conserved, that is no energy is lost. This is a fundamental theorem where whatever energy you get is the energy you give. Why is this important is in practical circuits, whenever you switch on, there is a little bit of energy that is lost due to heat. You don't have 100% energy transfer, but because it is so minute, here we can assume that the energy which is pushed is negligible and it won't interfere with our calculations. So we make an assumption that energy is conserved. Now, due to assumption A, what it says is the power consumed in devices should be 0. The total power in that system should be 0. This is what Tellegan theorem says. And we can try to solve one simple numerical to calculate it. So we have the system, and in this system what we need to do is we need to calculate we need to prove Tellegan's theorem, or we need to calculate what is I naught is the question. So for P naught, okay, it is 6 volt. The current is entering the negative terminal, which is wrong. For the passive sign convention says it should enter the positive terminal, therefore it is -2 and the power is 12 amp. Okay, similarly for P2, this thing, it is 10 into the current should have entered the positive terminal, so it's -3, that's -30. Similarly for P1, current is entering positive terminal, no need to change. 6 into I naught, that is 6 I naught. For P4, the current is entering negative, it should have entered positive, so P4 is nothing but 12 into -9, that is -108. Here for P5, I think P3, the current is entering negative, it should have entered positive, so -8 into 4 volts, that is -32. P5 is current is entering positive, no need to change the direction. 11 into 8 Ix, but what is Ix? Ix is 2 ampere. This is a current dependent voltage source, so replace the value of Ix, it's 176. Now when you do all the summation, it should come to 0. This is what Tellegan's theorem says. So when you solve this is equal to 0, and when you finally solve I naught, you get it as 1 ampere. You can try this numerical once for yourself, and we will meet in the next video where we will be solving problems. Thank you.